How are we all doing today? Awesome. Doing all right. Mighty fine. Ooh, even better. The morning class got to hear my 1-year-old screaming, so maybe you guys will get that too. Cool. Almost time.
Sorry about the mess.
All right. Got people starting to file in. Good, good, good. Welcome. Is that a Dorito or a pizza? Doritos chip. There we go. Can we donate bits for crates? Oh, that's fine. No. But I like the intention. That's for grades. I love it. Alright, it is 1 o'clock. So, welcome back to day 2. Glad that you are all here. And looks like we got about another 20 or so people that are waiting to come in. So, if you're running late, obviously the video, you can watch it at any time. But I just wanted to do a couple of administrative things to get out of the way before we get into it. So, Friday, excuse me, Friday we're going to be doing our lecture over Zoom, actually. So I was thinking about doing Blackboard Collaborate, and morning class overwhelmingly wanted Zoom. So, in reading all the Reddit threads about how much everybody hates Blackboard Collaborate from a student perspective, and all the problems, we'll give Zoom a shot. I will put out all kinds of information in an announcement to you guys so that you know exactly what we're going to do. Point for Friday is that we're going to form project teams. So you're all going to be able to introduce yourselves. We can see who's in the class. That way you're not just, usernames on a screen. It will also do a little bit of an in-class lab as well. So we're going to get some experience with Git, basically. If you've used it, awesome. If you've never used it, welcome to the world of source control. We're going to be using it all semester. So that's basically the plan for Friday. And again, later I'll put out an announcement with the link, everything that you need to know. You don't necessarily need to go on camera or mic if you're not comfortable with it, but just be aware that it would probably help out if you can at least introduce yourselves to everybody else. So, as planned for Friday, and again, are we going to form teams during class? Yes, so that's the plan for Friday, because that's actually going to be part of your homework. So, a couple of things in Blackboard 2 then. So I added a couple of extra links this is under course information. So we have our calendar, which should hopefully be helpful for you all to track your assignment deadlines and what's going on. I said I was going to do this after the last class, but basically I'm going to add in Friday is going to be Zoom. So I'll try to fill this up with what format the class is going to be. I don't want this to get confusing for you all, because I know how much of a pain that can be with too much information here. So we have a calendar. If this works out for you all, wonderful. If you're having problems with it, let me know. But basically, this seemed to be the best way to get you what deadlines are coming up. So you can see tonight we have that FERPA release form coming up due. Friday, your exam preferences are due. I'll make the exam preferences extra credit if you submit them. And Tuesday night at midnight is your first homework is going to be due as well. And again, that is in not assignments because you can't actually see that. I'm not going to use that. It just doesn't exist right now. It's under our folder here, under this line, and we have our first homework assignment. So everything's due at midnight for me, basically. So you basically have a whole week to do it. And just to kind of go over the format, since obviously you've never had homework with me, you don't know what to expect. I just wanted to show you what the plan is here. So it's 50 points. So just, it's a decent chunk of homework grade. Usually they're like 50, 75, 100 points, something like that. But what I'm looking for here is I'd like to know your Discord name, I'd like to know your GitHub name, because we're going to be using GitHub for the term project. And I need to know who's who. So I'm going to be looking for that information. I don't necessarily need to know your Twitch name, so that's why I didn't ask for it here. The last question is to form a project team. That's why we're going to do the meet and greet on Friday. Why you have until next week to get the homework due, so you don't have to fill this in right away if you don't have a team yet. Obviously, a good chunk of you probably don't even know each other or know what you're interested in. You don't have to have a project idea yet, but maybe some kind of a shared interest would be helpful for your teams. The last thing then, which is basically the bulk of the points, is going to be an ethics reading reflection. So we're going to talk today about a little bit about ethics, and we'll talk about ethics in more detail next time we have a lecture. But here we're going to learn all of the things that can go wrong with software engineering. And I want to know what your perspective is, what your response is to these things. So for each of these topics, so I've got some articles up in Blackboard in that folder. We're going to talk about Therak 25 today. Boeing and Tesla are separate articles for you all to read. I'm just looking for who's at fault, why are they at fault, and what could have been done differently. Because basically, software engineering is going to be a process where if things do go wrong, it's super important to figure out how we can avoid that in the future, right? So if it's a simple app and it crashes on startup, you're just going to be annoying people. But if you're, writing air controller software or I guess air controller software or fly-by-wire or brake-by-wire or any of these programs that have some kind of a mechanical implication or you're interacting with humans, that could be very bad if things go wrong, right? We're going to talk about that today. I like to call this my scared straight lecture. So um, basically, I'm just looking for your input here and what your thoughts are. So that is the homework. Make sure you put your name on it so that I know who's who. Always helpful. I'll get that from your submission anyway, but usually it's a little easier in here. And that's about it. So you have a week to do it. Any questions or concerns on that? Oh, and the other thing I forgot to show you too, sorry. Course information. Somebody asked last week how we can see who's in the class, which is a wonderfully valid question, especially since you only see Twitch names right now. There's this class roster link here, and it's blank. This is one of those lovely oddities with Blackboard where if you want to see who's in the class, you have to search for them. So you just click go with nothing in there, and then you see all the users and email if they've elected to put it in there, basically. So here's all of the people in your class. You want us to submit the Word doc to Blackboard? Yes, that's exactly what I'd like you to do. Just fill out the Word document, answer the questions in line, and then upload it to Blackboard. Yep. So, which ones are we supposed to read? I glossed over that. Thank you. So in Blackboard, ethics, ethics articles. So there are 4 articles here. So these three, the bottom three, so 30 years later, machine into monster, killer bug. So these are kind of the important ones. They're a little bit shorter. You can see they're in the kilobyte range. The first one here is the longer one. You don't have to necessarily read that one, but it's more of a for your benefit or for your knowledge. So this is kind of the like the long and detailed investigation here. Can I? Okay, good. Yeah, it's 24 pages long. You don't, it's basically a academic article. So if you want to read what these guys look like, um, I didn't sign in, that's why. It's a little bit drier. The other ones are more, like the newsworthy kinds of things. I think one of them was a Medium article. But if you want to know more, we're going to talk about this in detail today. And it's very important for you all as budding software engineers to know, what can actually happen. So yeah, then here we have a disaster. Well, there's obviously multiple disasters now at Tesla. There's also the 737 MAX article as well. So these are all, this is kind of the underbelly of software development, the dark side that nobody ever talks about, right? It's easy to learn new skills, new tools, new, machine learning models and just plop them into your program. But if you don't actually know what they're doing, we can have catastrophe happen. But we'll get into that. We'll get into that today. So, before I wobble on for too long here with that, let's actually get into our content for today. So we ended last time I was asking you in the slides. Okay, there we go. What programming languages do you know? This is more just kind of for my benefit and your benefit. It's kind of neat to see what everybody knows. But the interesting thing is that for software engineering, it really doesn't matter what language you program in, right? They are all going to be telling the computers to do something, right? I like to tell people that when they come to me asking for help with their programs and they're like, well, here's the code, like, why is it not working? Well, it's doing exactly what you told it to do, right? You screwed up your if statement, so it's ignoring your if statement or what have you. Software engineering is hopefully trying to reduce these problems. Now, software engineering is going to be the study of the process, right? So programming is like 10, 20% of your actual job. You're going to be mainly doing requirements, you're going to be doing meetings, you're going to be updating people. Basically, software engineering is going to try and make your software as safe and as correct as possible while still handling the personnel implications. So how many people do you need to hire? How many what's blooping on my computer? Oh, I'm not used to Outlook's blooping sound yet. I'm more of a Gmail person. Um, but yeah, software engineering is going to help us structure our development processes here. Okay, I'm going to gloss through this a little bit. Basically, the point is that as time goes on, so starting in the 40s and even before when we knew about computing topics, things get more and more complicated. So we start with assembly language, go to transistors and operating systems, and we get into, well, now it's the 2020s, but we get into autonomous vehicles, we get into Internet of Things, we get into worldwide computing networks. We're even shooting data out into space. I don't know if any of you watched the SpaceX launch and the live streams from the ISS, but we're live streaming video into outer space. How cool is that? And it's all because of this like foundational work as we go. So things are getting more complicated. Software engineering is becoming more important than ever right now, right? So one of this is a nifty little graph to show that software is actually increasing in cost as time goes on. Hardware is decreasing in cost. Does anybody know why that might be? So just go ahead and type your answer in the chat, for instance. Why software is so much more expensive than hardware these days? Sorry if I shouldn't be bouncing. I should be doing the Dora the Explorer where I just stand and blink. Cheaper, more efficient ways to make tech. Hardware is being made cheaper, question mark. In general, yes. And Sad Cat, also a great answer. So with hardware, we can commercialize it, right? So if we can figure out exactly what components we need, what gates and connections and all that, usually we can move it up to the manufacturing level. Now, if you're getting into specific specialized electronics, handmade PCBs or, whatever, it's going to be more expensive, right? GPUs fluctuate in price, but if you have highly specialized hardware, price is going to be high, obviously. more so if it has to be a specific grade, like medical grade or industrial grade or anything like that. But point is that software is going to keep increasing because A, yes, it has to be made by people. It has to be maintained by people. We don't necessarily know how many we're going to need to hire for any of the activities we're going to be talking about. Basically, software is kind of coming into its own, and it's still very use like developer oriented in a way too. So why is it hard and why is it expensive? Isn't it free? Haha. Hardware is not free. What we're actually seeing is that hardware becomes expensive the longer we have to maintain it, which I don't have on the slide. Mouse needs to go away, although I do need my pointer so that I can do my little professory, hey, look at this thing. Um, but the number of features increases, meaning the number of checks that we have to do to make sure no features are interacting with each other weirdly. The number of inputs, we have to handle the outputs as well. There's just so much going into it. And we're going to need people to manage that, right? And we're going to need to pay companies for licensing or whatever you're going to have, right? So there's a lot of factors that go into it here. Oh, outputs is just hidden. There we go. So anytime that we have an increase in any of these, we're going to get some kind of a dimensional growth, right? So if we look at some of the different software applications that are out there, again, this is one of those ones where this is more to show an increase in scale. Let's start with a trivial program. Okay, 500 lines of code. This is your first ever project. If it is in something like Node or Java, it's probably 500 lines to write hello world after you do all your imports and package declarations and all that fun stuff. Um, Obligatory snipe at Java, obviously. But as you go, the time increases, the number of programmers increase, the number of lines of code increase, things get more complicated, right? If you're doing unit testing, integration testing, really, whatever kind of testing you're doing on a 500 line of code project, that's going to take a lot less time than, say, a 35 million line of code project that's been written over the span of 15 years, right? So the complexity here is staggering. One of the great examples of these kinds of interactions is that a while ago, there was a Ford vehicle where I don't know if any of you ever worked in automotive or know any of that, but there's all these different subsystems in cars, right? There's the window controller, there's the body controller, which is basically like your entertainment system, engine control. So there's a lot of different bits and pieces in cars. And now they're even getting crazier and more complicated. There was one particular, it was either during development or like release testing or something where if you tried to open your window, it would turn on the windshield wipers. Right? And why is this happening? This is the most bizarre interaction we've ever had. Well, they're all reading from the same shared data bus. And the window controller is sending out data, and the wipers think they're being talked to, so they turn on. Now, trivial problem, annoying problem, not horribly dangerous, but an example where things can happen that you don't necessarily expect. As the scale increases, all of these different edge cases have to be treated, you know, not identically, but they all have to be handled, right? So scale up to worldwide healthcare systems or intelligent transportation systems where your buildings are talking to your sidewalks, which talk to the cars, which talk to maybe your smartwatch or something like that. And you have this huge distributed environment that you have to manage. And how the hell do you do that? The scale is enormous. What you can do, and where software engineering is coming in, is you need a process to handle this. There are a ton of processes out there. Everybody has their own that they love, whether you're more of a traditionalist, you like waterfall or the V model, you like the new and exciting things like Agile or Scrum or any of these cool new things that everybody's jumping on that bandwagon. Um, Whatever you use, the point is to follow that process. Okay. There are pros and cons to all of them, and we'll talk about that. But the important thing is that you follow your process and make sure that all of your activities that you do, so validation, verification, working with your customers, doing your development, all of these things are super important. Now, here are a few examples. So there's a missile that we're going to talk about here. There's a baggage system where basically a whole bunch of baggage went missing. Well, that's controlled by software. Therak 25 is the one that we're really going to dive into. but we're going to basically see what happens to software when it goes wrong. And again, not just impacting people, but think of scheduling and cost estimation and budgetary issues. These all go into a project. What you're basically going to learn here is that software engineering is a business process at the end of the day. It's not just I'm going to hack out a few 100,000 lines of code over the weekend and release my super cool hobby project. Um, Real world projects are just more than programming. I think I said that last time too. All right, so the depths of despair, I guess, area here. In case studies, well, some of these, one of them is super disturbing to me. Some of the other ones are like, huh, that's horrible. But this all happened in the real world, and they're not all that far removed that it's not like recent. So, first one, the Ariane 5 missile. So, this was a rocket created by the European Space Agency a while back, and it took 10 years to build. So, 10 years worth of engineering effort. So, bringing together rocket scientists, programmers, engineers, and everybody's in on this thing. $7 billion to build. So, this is a pretty good chunk of change. A minute after it launches, the rocket explodes. So after 10 years of building and testing, the rocket is in the air for 60 seconds or less and then gone. What happens? This happened because somebody tried to put a 64-bit number into a 16-bit variable. Now, if you have no idea what this means, it means that you have a very large amount of data that can be held by a variable, and you're chopping off most of it. So you lose all that decimal precision. Okay? So now all of these controllers in this rocket are operating on data that is no longer precise. So problems are bound to happen. So this is, am I out of the way this time? Okay, good. There's our rocket. So could this have been solved prior to release? Absolutely. But this is just one of those things that probably came up as a warning in a compiler, might have been ignored. Um, I don't know exactly what is happening behind the scenes. No, this was just a rocket, so it was unmanned, fortunately. But still a large loss of money, basically, for the ESA. So this is one thing that, one example. We have a recent example too. Does anybody remember the Mars rover that crashed? That was fun because one group was using metric and one was using imperial, and nobody ever realized there was a difference. This was a few years back now, but yeah, that was another space-based example. So this is the first one here. Next one, Toyota Prius braking. So this was several years ago. The Toyota Prius, the lovely hybrid car, which was going to change the world, had a brake software delay. So what's happening here is that you press your brake pedal and you're not braking as quickly as you think you are. Okay? So if you're going at 60 miles an hour, you press your brake, then you don't start stopping until 90 feet later. 60 miles an hour is what you go on most, highways, like Lake Michigan Drive or, any of the numbered avenues where there's no speed limit. You're going 60, you press your brake and then you don't stop. You're kind of in your oh shit moment. um, this is a huge problem. Now, why is this a problem? There is a lag in the anti-lock brake system, which basically balloons throughout the system and causes all kinds of problems. So if you've taken an operating systems class, think of like a real-time operating system where everything has to follow a set schedule. And if you miss your schedule or you miss a deadline, things start getting delayed and problems start building up and up and up and up. Same thing here. We have a huge problem which honestly could be solved, but nobody noticed it before it went out. Okay, and then the last one here, which we're going to cover, is the Therak 25. So this is one of the articles too. Um, this is a landmark case study for software engineers. And unfortunately, people have died or have been horribly maimed by this. So that's the warning up front. So this is a chemo machine. Basically, you're blasting people with radiation in an effort to kill cancer cells. And this is an iterative project. So the Therak 6 was the first one, the 20 came, and now we have the 25. All right. So the difference here, though, is that this new model, and this new is the early 90s, late 80s, there are no more mechanical safety measures here. Everything is controlled by software. And moving everything to software is kind of the idea in that, well, it's cheaper, it's quicker, it's more easily controlled. Software is not going to degrade. Whatever your reasoning is, let's move everything to software. We're seeing this now again with autonomous vehicles, by the way, which freaks me right out. Um, but what we have here is that everything is software controlled, including the safety mechanisms. Okay? So, what do we think is going to happen if I'm talking about a case study where everything is controlled by software? Bad things are going to happen. The thing I will mention, though, is that this machine was extensively tested. It was verified and validated over several years. We have lots of hoops to jump through for medical applications. And in theory, it should have been no problem. Cracks are starting to show, though. One person wrote the entirety of the code. The further problem, which I'll come back to in a moment, that same person also did all the testing. Like the water tankard. Thank you. It's a um, leftover from some time in Germany. I needed a big tankard for class. So, um, what happens when you test your own code? Think of it also what happens when you edit your own papers. You're gonna miss things, right? You have like this laser focus. Yeah, that's the exact word I'm looking for. Thank you. You don't think objectively. I'm gonna write all my test cases to pass. I'm not gonna think of all the weird combinations. Exactly. You don't know what to expect. You are not other people. You are not going to test some weird combination. Um, and the hardest thing to keep in mind too is that you think like an engineer. You think like a programmer. You think logically, maybe iteratively or something like that. Not everybody has this mindset. They're going to do things way, way differently than you. So it's always good to have, well, it's pretty much required to have other people test your stuff, but it's always good to have outside perspectives. Other things here too, unit testing, general testing. So basically all of our test procedures was more minimally done. So we did enough to pass everything. We met all standards, but we never went above and beyond here. So effectively, there are a huge number of problems with this particular study, which is why we talk about it. So there are 11 units installed between the US and Canada. So we have two different countries involved here with, two different overseeing medical organizations, and they released them all. And then through this process, there were 6 massive overdoses of radiation reported. And I'm sure that we all know that if you get radiation applied to body cells, really bad things happen, which is why we use it to kill cancer cells. But if you overdose, it's even worse. So, why does this happen? Well, I mentioned there was the Therak 20 in between. It was a step in between fully mechanical, partially mechanical, completely software controlled. The Therak 20 had hardware interlocks, meaning that there are safety mechanisms controlled by hardware to prevent any kind of overexposure. Okay? The faults that caused this to happen in the 25 were present in the 20. Nobody knew they were there because the mechanical system was blocking it from ever happening. So you take away the hardware, you lower cost, which is obviously the benefit of why they're looking to do this, but now there's no safety net. Okay, so that's what happens here. Get the mouse out of the way. And if you're looking for the technical side, what's really happening here are race conditions and concurrency errors. So again, if you are doing any kind of parallel processing or any kind of operating system programming, we never want a race condition or concurrency error because that's when we're trying to access shared memory, right? You do that, We have no idea what's going to happen. We don't know if the variable state's going to change. We don't know who's going to get what data. Um, and there are innumerable things that could go wrong when variables access bad data, basically. And what happens here, too, is that it's not just the programmers. There is also a human aspect, too. This was intended to be used by people. It was operated by people, and they also have some responsibility here as well. First, the medical staff that was using it didn't think the machine was causing the problem. They trusted the programmers. They thought this was a safe machine. There's no way that this thing could be causing it. Some other problem must be occurring. Um, and they kept using it and using it and using it, and that's why we have multiple cases here. There is also improper training. So what's going on is that the medical staff are trying to get through their sessions as quickly as possible, so they hit the button super fast. And what's happening is this is going into an incorrect power mode. So you have like an old style terminal system, like a VT100, if you're familiar with that. What they're trying to do is to make their job go as quickly as possible. So those of you that are keyboard jockeys probably have, keystrokes memorized that you're going to do super quickly. You don't even have to think about it. That's what they're going for here. Let's hit the X, go to 25 MEV mode, cursor up, then E, then 25, then enter within 8 seconds. Nobody thought this keystroke sequence would happen. Um, so basically this problem went unnoticed. But what we see here is that people are trying to go through their jobs quicker, which is expected, but the system can't handle that. Nobody tested this case. So we have improper training, we have improper coding standards, and we have just basically a whole mess here. There are some lessons though. The engineers were not incompetent. Okay, there's a lot of testing, there's a lot of rigor that went into this system. What this does tell us is that our testing procedures are never done, right? If you release something into the world, you still have to keep maintaining it. It's impossible to consider every single issue that exists, but when it manifests, you have to go back and fix it. So maintenance is always going to be an important aspect of software. Now, could we have solved this? This being all of these problems. I don't know if any of you are familiar with the lint. It's basically one of the static analysis tools where you check for variable precision, you check for data types, you check for coding standards. One of the more annoying lint results that I used to get in industry was I forgot the else case for an if statement if I never needed an else case. But our programming standards had that if you have an if statement, you need an else, even if the else is empty. This is more of a, just kind of a programming guideline here. So, could we have saved the Ariane 5 explosion? Possibly. Lint may have caught that or some other tool. Could we have done extensive testing, whether human-oriented, getting anonymized focus groups? It's possible, but the issue is that we never necessarily know exactly what's going to be wrong, right? If you run all of your tests, everything comes back green. That just means you haven't found the next bug yet. It's out there somewhere. And it's the sooner that you realize that it is inevitable that a problem will crop up, probably the more stronger of a designer you will be, a programmer you will be, honestly, because there's always going to be something that happens. And it's always going to be somebody else that tells you what it is. It's not just you finding them. But the point is here that it's important to do as much as you can before you release it to the general public, right? So, um, what's going to happen here is that this is where I'm going to make my case that software engineering is the most important class that you will take. It doesn't have to be my class. That'd be a little bit egotistical, I think. But it's important in terms of the content. So you're going to learn how to program. You're going to learn how to do amazing things with computers. But the important side is making sure that everything that you have out there is rigorously tested, that you followed a correct procedure to make it, right? It's so easy to bang out a program and just release it up on GitHub. The problem is if somebody else takes that and there is something that can cause harm to them in some way, right? You make a fired app, that's great. You make a engine controller with a glaring problem, that's a different issue. So where's the excitement here? I had a lovely comment from the first session this morning that they joined the computer engineering program for the sex appeal. Um, this is going to be historically the driest stuff you've ever heard. We're going to talk about specifications, we're going to talk about processes, models, we're going to talk about UML, all the stuff that you're going to go, oh, this sucks. But it's the most important thing that's out there, even if you don't do it. Yeah, GV student went down for me. GV is, what's GV student? Is that, not familiar with that, I guess. But, mm, sorry, the Wi-Fi. Gotcha. Yep, that makes sense. Well, if Wi-Fi does go down, at least you can kind of go back in the recording, hopefully. Um, my Wi-Fi's been pretty good so far. That might be a good point, though. So if for some reason our internet goes down, what I will probably do is I'll finish the recording and put it up there so that at least you have the material. Um, that's one thing I'm slightly concerned about is if my internet ever goes out, then I just disappear. So let's talk about excitement and whatnot for software engineering. Keep in mind that the exciting stuff, the really cool stuff, is when this rocket does not explode. The software engineering is what prevents that from happening. I fall on the side of the engineer is super important in the term software engineer. I honestly think programmers should have to go through the professional engineering program just because all of the other engineers that had to work on this probably had a professional engineer's license, and programming it is just as important. So keep in mind that, once you get into programming real applications, you're going to have an impact on other people's lives. Okay, maybe it's not as catastrophic as a radiation machine or a rocket, but what if you're working on an ERP system and you accidentally misplace somebody's entire paycheck, right? There are so many implications that software can have on other people, and it's very important to take it all seriously. But still have fun programming. It's a super fun job, I think. I love programming. But to make it a little more somber, so let's assume that you were the programmer that made the Therak. You are indirectly responsible, or directly, depending on how you look at it, responsible for all the problems that happened. People got severe radiation burns. There was one breast amputation that had to happen, and at least one person, I'm not sure what the current number is, but there was a cancer, virulent cancer, that was the cause of death as a result of overexposure. So just trying to say it's not all fun and games. It can be very, very important. All I'm asking is for you to be responsible with whatever you program. Um, that's pretty much the end of my soapboxing there. Um, so we're going to talk about software engineering in terms of the real world. So let's talk about it. What is software engineering now? Okay, we've seen, I gave you the intro spiel, spiel, pronounce it correctly. We've seen what can go wrong. Now, what is it? If you take away anything, understand that software engineering is a process. Programming is just one piece of that. We need to consider um, maintenance. So what happens after you release your software? You need to work on a team. You need to develop all your requirements and use cases and test cases, system models. This all goes into a single software package. You're going to moan about the model aspect, who uses UML models? Well, the system analysts do. And people have used models at the code generation level too. So it's super important that we actually know how this all works. And it also, honestly, even if you're not doing something safety critical, all of this information is useful if you want to get a project up and running. Rather than just going right into coding, take a few minutes and think, what are the use cases, right? Who are the users and what do they care about? Right? You're making a phone application. You make it to your specifications, right? So I've got my boop 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 awesome phone app, works great for me. Nobody else can use it because you designed it for you, the programmer, not you, the common person who has different things, different priorities for their applications. So there's lots of aspects that go into this here. Now the problem is that regardless of what process you use, pick your favorite, use whatever your company uses. If you screw up any of these phases, then things can go awry elsewhere, right? You mess up a requirement, that bubbles down into your program. You screw up a design decision, again, there's an impact at some point in the process. So some of the laws which are kind of fun to talk about. Me as a sarcastic and jaded person, I'm going to kind of speed up a little bit here so that we don't run over time. Um, I specifically like Murphy's Law because it applies to everything everywhere. If anything can go wrong, it will. The sooner you start planning for failure, the better, as horrible as that sounds. And my other favorite one here is Brooks' Law. So the more manpower you add, the longer your project's going to take. So don't have three programmers on your team, add two more, and expect it to go quicker. That's not how the world works. Um, why does that not work? You have to bring them on, you have to onboard them, you have to get them used to the process, figure out the whole framework, and then it can become difficult rather than to treat your programmers correctly. So none of you go into to business and just think you're going to throw more programmers at a project. It's not going to work that way. I also like this one. Software gets slower, faster than hardware gets faster. So it's very, very easy to introduce bloat into our programs. Um, just look at anything written in Node or um, anything in Java. But yeah, I feel like computers are getting slower way too quickly. All right. I'm going to kind of go through some of these slides relatively at a high level and quickly. The point is that we have this notion of an engineering process. So this is a very famous model of engineering evolution. Basically, we're starting at a craft level and we're getting to engineering. We're going to see this model a couple of times here. So we start with some craft, right? You are making the next great widget. You have made one. It took you a lot of money to make this one because you used the best materials. You gave it so much of your time. You had to make everything by hand. Basically, you are a virtuoso with this widget, right? But now 500 people want to buy that. If it took you a month or two to make this thing and a ton of money, it's never going to be affordable for everybody, right? That's craft. If you're a home brewer, you have your craft brews. These are, well, obviously now they're basically macro production stuff, but um, these things take time. When we start scaling things up to production, that's where we start analyzing, how we can make this quicker and faster. So if any of you ever make any kind of things for like Etsy or the web, you might go out and buy a CNC machine or a laser cutter or one of those the Crickets where I don't have to use an X-Acto knife to cut out vinyl. I can just print it, right? So that's where things like production come into play. When we join these two together, we get commercial release where we can start scaling up. And then maybe we bring in a little bit of science here. So how does this work? Why does this work? So this thing that you created, I'm just going to call it a widget for now, for lack of a better word, we start understanding the underpinnings of it, right? You start understanding the physics of it. Consider this in terms of something like a civil engineering tree, which I actually have in a couple slides, so I'm kind of cheating in terms of topics. But you start understanding the statics and dynamics of this object, then you can take that and turn it into an actual engineering field where you can go through all this process modeling. We can hammer out the details of exactly how we can feed back this into our production line. All right, so again, the craft side of things, let's start out with a large pool of talent in like one or two people, right? We're just trying things, we're brute forcing everything. We're not going to the very esoteric or crazy algorithms which are going to help us run it faster. We just want to get this thing done and out there, right? Maybe it's for personal use. You start going into production, then you get into procedures, you get into refinement, you go into cost reduction mode, basically all of these things which make us able to scale up. Okay. Then you get into the professional engineering where we get to the end of this timeline here. Let's talk about the theory behind it. Let's talk about the science underpinning it. So how we can maybe make a better second version or third version or something like that. Think of strength of materials where we might use aluminum or steel or. You only get to that point when you understand the theoretical underpinnings of it, right? So we see the same thing here in civil engineering. You start out at the olden days, let's invent fire and the wheel and all that. And then we take that and we build and we build and we build. The Romans get their aqueducts. 1700s, we get into learning about materials and properties of those and their strengths and weaknesses, what causes steel to flex versus crack. All of this goes in here. And then finally, we get to our professional civil engineers. We can build bridges and just hammer them out on a production line, right? This might seem kind of nebulous and very high concept, I guess, but this is actually pretty easy to see if you look back at history in terms of how things evolve over time. Just kind of the nice thing about hindsight, I suppose. Where this impacts you all is that we have the exact same model for software engineering. Let's start out with our craft. Let's bash together ones and zeros and make a theremin or something cool like that. Let's start making what's Pong on a oscilloscope. Somebody recently ported Doom to the oscilloscope, which I thought was kind of fun. But you start out with some crafts, hobby programmers, people wanting to learn a new technology. We make something cool, but it's not extensible from the Apple to the IBM, or if you want to get into that area. Let's start bringing in production. Let's start ramping up our development methodology so that we can get as many people in front of this software as we can. Let's make it commercialized. Let's release operating systems. Let's release all of our stuff at a high level. Well, turns out we have some science here as well. And you're all taking this in your other courses, right? So algorithms, your digital logic, learning all these crazy new database paradigms that are out there. I really feel for you since you're going to have to learn so many interesting concepts. Like when I was an undergrad, it was let's just do relational databases and we're done. Well, now you need to know relational, you need to know NoSQL, you need to know graph databases, depending on where you're going to work and what the application is. There's just so much more high-level science that's out there. Let's move my bullet right on the eye. Perfect. Science. And then we take the science, right? And let's go to the engineering domain. How do we take all of these algorithms, all these underpinnings, and make a space shuttle, right? How do we make something that can pinpoint land on a raft or something crazy like that, right? So this is where all of our progress is happening. And we have this exact same evolution model for, any engineering domain. It's really cool to see. So to kind of wrap this up here, because we're coming to the end, is that for software engineering, you're going to find there's basically two pillars. Okay, there's the process, and then there is the theory. We're going to focus more on the process in this course. This is the things that you need for industry. This is going to be the things that you need in everyday life for programming. The theory is going to be your graduate level classes where, we can sit around and talk about what's the benefits of agile over waterfall and a very theoretical concept in terms of prototyping and salary and all that fun stuff. But here we're going to talk about mainly what you need to know to be successful. And what we're going to get out of this are the different phases of software engineering. This is basically going to be our whole semester. What are we building? That's the definition of your project. How are you going to build it? Did you do it right? Did you maintain it correctly? And then some extra things like staffing and, which we'll talk about in a minute here. But this is basically software engineering in a nutshell. So we have our requirements. You have to understand your domain. This is all stuff, again, that we're going to be getting into very soon. Things like project planning. If any of you ever done a Gantt chart where you tried to plot out your time, these are all things that are part of software engineering. And this is kind of where I said we have some dry stuff in here too, but keep in mind that it's super important. Just kind of skipping through a couple of little not normal, but very high level slides because we want to make sure that we talk about these umbrella activities because they're kind of important and that each of our different software engineering phases have these. So you're going to have reviews. This could be with other programmers, it could be with users. Basically, you're trying to make sure that your software is operating correctly for that state that it's in. Now, you can do requirements reviews. It doesn't just have to be code. Documentation, you're all going to come to know and love writing documentation. But version control and configuration management are basically what we're going to be talking about on Friday when we do our Git lab. But let's track our software over time. Let's commit our software so that we can go back to various versions, or we can specify this is my release candidate for 2020, September, whatever, whenever you have to do a check-in, right? So this is all going to be a big aspect of it here. Now, if you don't believe me when I say maintenance is super important, that's fine. But here we have a nice pie chart with no source, so that means it's correct, or it's obviously correct, right? But here what we have is the proportion of engineering costs for a project. So blue here is when we're defining our project. So this is step one. Orange is going to be, looks like it's about a quarter of it. So this is your development and verification. So I'm programming it, I'm testing it, and verifying it. The rest of this pie is maintenance. Is your software still working correctly? Are you promising future updates? So on and so forth. And further, if you don't believe me, here's the cost of fixing software errors throughout the process. So here at the requirements, design, implementation phase, this is how much it costs, on a general scale. So we don't have numbers here, but basically costs go up the longer in the process you are. Think of it this way. If I give one of you an application, it's going to cost a lot more to fix it after you have it rather than before, right? That should be more of a common sense kind of thing. Anyway, so I have, we talked about the homework at the beginning, so that's due next Tuesday night at midnight. You have the two little things, so the ethics, or not the ethics, the exam preferences and the FERPA form, those are all due. Anybody have any questions for today before we end? Kind of ran through it quickly there at the end. I wanted to make sure we got through everything. So unless there are any other ones, so just a reminder, so Friday, if you came in late, we're going to have a Zoom meeting so that you can all learn about each other, and I can learn about you too, because it's really weird having class and not being able to see all of you. But we'll do that. Monday, there's no class. If you're not aware, so Monday's Labor Day. Kind of looks like an eyeball here. Neat. Did you say next time you're going to form groups? Yes, so groups will occur on Friday. If you already know who you want to work with, that is perfect. Feel free to advertise in the Discord channel if you want to do that as well. I would like you all to be able to form your own groups. If we run into problems with that, I will definitely help you out with that. Won't have a mic webcam until next week. So X, I guess I will just call you X. That's fine, but please at least maybe try to join and participate via chat if you can, because you can chat in Zoom too, right? So uh, we will, yeah, if you don't have a webcam or a mic, or you're not super comfortable with that, that's fine. But please at least still join via chat so that we can try to figure out, who you are, kind of what you're interested in, things of that nature. So yeah, if you can join, that'd be good. Oh, you can use your phone too, so that's true. But yeah, other than that, I will, like I said, I'll put out an announcement and I'll try to cover all of that too. We'll give Zoom a try. I've used Zoom before for other things, so it should be fine. Like I said, I've heard so many problems with Collaborate that I'm kind of leaning towards just doing that on Zoom. But other than that, I will see you all Friday, and I hope you all have a good couple of days. So, have a good one. Let's see, ooh, I like this one. I don't know what the implications are of this guy, but he looks cranky and grumpy, just like me. Anyway, I'll see you all next time.